Hello everyone, this is Guru Purohit and I welcome you once again to another session of chemistry practicals. Now, in this particular session, the practical that we are going to consider is all about inorganic preparations. Okay, the title is Inorganic Preparation. Now, my dear friends, when we talk about inorganic preparation, so it's obvious that we are going to discuss about preparation means synthesis of inorganic compounds. Now here one more specific part which I want to tell you is the inorganic compound that we are going to synthesize is a complex compound, or we also call it as what? A coordination compound. Now what do you mean by a complex compound? I hope you know this very well, but just a recap, I'll tell you. A complex compound is a compound which involves two species, and that is metal and ligand. Ligand are electron donors and metal are electron acceptors. So combination of these two, it results in a formation of a coordinate covalent bond, and the compounds are therefore called as coordination compounds, or they are called as complex compounds. The ratio is between the metal and the ligand is 1:many. Alright? It's not 1:1. So we are using over here ligands. Okay, so the ligands combining with metal resulting in the formation of a complex compound. Now, in this particular session, the complex compound that we are going to synthesize is Tris-acetylacetonato ion, and the charge on ion is +3. So we write down in Roman number 3. Okay? Tris means 3. It's a complex. So it requires two species. When you talk about ion, the first thing which will come automatically into your mind is, yes, it's a metal. So it's very obvious now. The acetylacetone is a ligand. Okay? Now I'll just give you the structural formula of acetylacetone. We also call it as, in short, ACAC, acetylacetone, and it is given as this is, my dear friends, the structural formula of acetylacetone. Alright? Now here in this case, the two oxygen atoms that you can see, they are going to be donor atoms. So it means that in one molecule of acetylacetone, there are two donor atoms. And such acetylacetone molecules, how many we are taking? 3. And therefore, the total number of donor atoms is 6. Okay? And hence, we say that the coordination number of ion are 6. Because most of the time what happens? The students feel the number of ligands surrounding the metal is the coordination number. So here the students will say the coordination number is 3. No, my friends. It's the total number of donor atoms of the ligand attached to the metal is the coordination number. So here in this case, the coordination number comes out to be 6. Alright? I hope till this part is clear. From the coordination number, we come to know about the geometry of the complex. Now since the coordination number is 6, and hence the geometry comes out to be what? Octahedral. Right? Now, next point which you need to understand is the synthesis is based on the principles of green chemistry. Okay, we are going to follow the principles of green chemistry. Now, my dear friends, there are 12 principles of green chemistry, some of which I would like here to elaborate, and that is, number one is, in this particular synthesis, there is going to be a high atom economy. Now what do you mean by this? In simple words, it's greater the amount of the reactant being incorporated into the final product. Alright? Because whenever we carry out the reaction, generally we have a major product and a minor product. So if a greater proportion of the reactant is incorporated into the major product, it means that the amount of minor product is less. Okay? So that is what is high atom economy. Next thing is, the entire procedure that we are going to follow in the synthesis of this complex, we are going to use less hazardous chemicals. Okay, so that is number two, less hazardous, dangerous chemical synthesis is followed in this particular case. The next important point is that this synthesis, whenever we are going to carry out, we are going to make sure that it's going to be environmentally, because this is very important, my dear friends, the environment in which we live. Okay, so environmentally, it's going to be safer as well as cleaner. Okay, and because the atom economy is high, so we can also say it minimizes the waste, which is generally in the form of the side product. So these are certain point of views that is taken into consideration during the synthesis of Tris-acetylacetonato ion. Next point, my dear friends. Generally, whenever we talk about chemistry particles, general exceptional cases are there, but generally they are categorized into two parts, qualitative as well as quantitative. Now, whether a particular experiment is qualitative or quantitative, that depends upon the end result. Now here, in this particular experiment, the end result of this particular part is to find out the percentage yield. Okay, determination of what? Percentage yield. Now, what do you mean by percentage yield? That also I will make you understand. When you use the word yield, it is the amount of the final product, or what we call it as a major product. Percentage, so you already know, it's a factor of 100. So percentage yield is given as, the formula is the observed yield. Once we are going to prepare this compound, we are going to weigh it divided by the theoretical yield. Now in theoretical yield, we consider the reaction which is taking place on paper, and on the basis of the reaction taking place on paper, we actually find out how many moles of the reactants are being converted into how many moles of the products, and on the basis of this, the theoretical yield is calculated. So we have a practical yield, or we call it as an observed yield, divided by a theoretical yield. And because it is to be expressed in terms of percentage, so hence we need to multiply this by 100. So you can see here, my dear friends, the formula is, when you say percentage, so it is directly proportional to what? The observed yield. Okay, so the entire experiment is based on what? Weight of the major product, and that is this, Tris-acetylacetonato ion. Okay, and when I talk about weight, I talk about amount, and therefore I am very sure you got the idea that this particular practical or experiment, chemistry experiment, falls into the category of, yes, okay, it is quantitative analysis. Okay, it falls into this category of quantitative analysis. Okay, since it is based on what? Weight. Alright, so this is the initial. Now next thing is, we have to consider, because this is some industrial processes taking place. So in the industry, always remember, the major objective is from the economical point of view. Okay, there has to be profit. So whatever we are preparing, it has to be used. It's not that I am going to carry out n number of steps, I get a product and then I put it in the dustbin. No. So it has to have certain use, and that's the reason I am synthesizing it. So there are various uses of this complex, okay, which we are synthesizing. Some of the important ones I will make you understand that. The first one is they are used as effective catalysts in many organic reactions. Okay, that is polymerization and chlorination, that is halogenation and etc. In pigments, they are used as color stabilizers because the color has to be stable to heat, it has to be stable to light. So this plays a very important role in improving the color stabilization property of the pigment. It is used as a carbon scavenger, removal of carbon from the diesel fuel, and in a way it will try to reduce the environmental pollution. Because if carbon goes into the atmosphere and if suppose it reacts with incomplete amount of oxygen, insufficient amount, it results in what you know it very well, it's carbon monoxide. And my dear friends, carbon monoxide is more polluted as compared to carbon dioxide. Okay? So that is where it is being used as. It's used as fungicides. I'm talking about the uses, my dear friends, of this particular complex. So it's used, as I said, as a fungicide in extraction of metals. Okay, metals are going to be along with many other materials, so I need to separate that metal from the other materials, and I get the metal in a pure form, and the pure form of the metal has many industrial applications, and therefore it has a high commercial value. So my dear friends, on the basis of this, we can conclude that yes, this particular complex compound that which we are synthesizing is of immense use in the industry. Okay, it is also used in the rubber industry in the process of vulcanization. Alright, and hence the value of the entire synthetic method increases if the applications of the final product increases. Okay, so that's the reason I am making you understand, because many times the question is asked, okay, we are preparing it, we understand the theory behind it, okay, we prepare the compound also, now what to do next? What is the use of that? What is the purpose of doing all these things? Alright? So the purpose is you get a hand of how to synthesize complex compounds, and once you get that compound, you can use it in n number of places. Alright? So, my dear friends, I think you have understood up to this very well. Now, if I just write down a reaction which is not in terms of a molecular formula, okay, but in just in the form of wordings, then what we will say is that we have iron, okay, that is Fe. We are going to take it in the +3 state, so that means this is in a metal ion form. So Fe+3, we can take it in a chloride form. +3, my dear friends, you know very well, it is called as ferric. So we can take it as a chloride, so that's the best one. So ferric chloride can be taken along with the acetylacetone, and it results in the formation of FeAcAc thrice. Alright? Because as I said, the complex is what? Tris. Okay, so Tris-acetylacetonato it is. Alright? So this is a word reaction. Okay, and once you get this particular complex, you are going to take the weight of it. You already get the theoretical weight on the basis of the formula, on the basis of the chemical reaction, and then accordingly you can find out the percentage yield, which is the final result of this particular experiment. So I hope up to this part is absolutely clear to all of you. Now I will explain you the procedure. That means the steps involved in the entire synthesis, okay, step by step. And once the entire theoretical part is done, then in the second part of the video, I will actually demonstrate the synthesis of this complex. So here we start. Step number 1, and that is, we are going to take the required quantity, the supply quantity, FeCl3, that is ferric chloride. As I already told you, the complex contains Fe in the form of plus 3G. Okay, so ferric. So the supply quantity of FeCl3 has to be taken in a beaker. To this, we will be adding around 30 cm³ of 1 normal KOH, that is potassium hydroxide. Okay, and it is 1 normal. So we have to prepare the 1 normal solution of KOH. We are going to take around say 30 cm³. So that means, let us say it is approximately around 2 test tubes. Okay, you need to take it. But my dear friends, before you add KOH into the FeCl3, you have to make sure that the FeCl3 is dissolved in distilled water. Minimum quantity of distilled water. Okay, so please keep this in mind. Okay, it has to be dissolved in minimum quantity of distilled water. I just write down DW, so I hope you understand this. 30 cm³ of 1 normal KOH has to be added to it. Now this results in, we need to form the solution also, okay, so that precipitation can take place very well. And after forming, you will see that there is going to be a reddish brown PPT formation takes place, and that PPT is of ferric hydroxide, that is FeOH thrice. Okay. Now this precipitate that you get of FeOH thrice is not the only one, my dear friends. Okay, there is a side reaction also taking place, so that means the KCl will be formed, and that will be in a solution state, and this is in a PPT. Okay, so I hope you understand the difference. So what you do is, you make sure that the PPT stands as this for few times, that is say around 15 to 20 minutes. And as a result of which, all the precipitate will settle down and you get a supernatant solution. The solution which is at the top, and that is going to be what? Clear. And that is supposed to be what? Composed of KCl. Okay? So, the next thing is supernatant solution, which we have to decant it. Okay, slowly remove it, making sure that the precipitate is in that. And then, after decantation of the supernatant solution, what remains is the precipitate. Of course, some part of the solution will do remain, but the major part of the clear solution is removed. And now, we are going to filter the PPT by making use of a Buchanan funnel and using a Whatman filter paper. And it's going to be number 1. The numbering depends upon the pore size of the filter, and the selection of the filter paper depends in turn about the pore size of the precipitate. The pore size of the precipitate, the particle size of the precipitate must be greater than the pore size of the filter paper. Okay, so that is what you need to keep in mind. So my friends, you filter the PPT through the Buchanan funnel, okay, by making use of Whatman filter paper 1. Now what you do is transfer the PPT in a beaker and add to it around 5 cm³ of acetylacetone. Okay, we are going to add what? Around 5 cm³ of acetylacetone, which is going to behave as what in this particular complex? Yes, it's a ligand. Okay, so Fe is a metal which is in the +3 state because the PPT is a composition of FeOH twice. So Fe is in the +3 state. Now it is going to combine with what? The ligand, that is acetylacetonato. Okay, so as a result of which shiny red crystals are obtained. They are slowly being developed. Okay, and it has to be cooled in an ice bath for say around 15 minutes, and then they need to be filtered once again through Bucknell funnel, obviously containing a Wattman filter paper number 1. Okay, once the filtering is being done, we need to carry out the washing also. Okay, with respect to distilled water and alcohol. And once the filtration is done, once the washing is being done, the next step is drying. You need to dry it in vacuum over calcium chloride, which is going to be present in a desiccator. So that is going to absorb all the moisture which is there in this particular recipe. And this is the way. Absorption of moisture results in drying of the compound. And that's why we use the word what? Dry. And finally, yes, the most important thing is weigh the complex. And the weight of the complex that we get is what I was referring to few minutes back in the form of the observed yield. Okay, theoretically we will calculate on the basis of the reaction. Okay, that is being written. So observed upon theoretical, and then you multiply it by what? 100, and that is what our final result is, and that is percentage. Of course, the calculation part I will explain to you in the later part of the video, but then this is what our aim is. Okay, so this is the theoretical explanation of how to execute the synthesis of this complex. So I just take a quick recap. First of all, what are we going to do is, we are going to take ferric chloride, which is in a solid form. Okay, the given quantity, whatever the amount of that is, and we are going to dissolve it in minimum quantity of water. Next, what are we going to do is, we are going to add into it around say 2 test tubes of 1 normal KOH. Okay, warm it if necessary, and that will result in the formation of a PPT. That means ferric chloride is getting converted into a reddish brown PPT of ferric hydroxide. Alright, now allow that particular precipitate to stand as it is for some time. So all the precipitate will settle down and the clear solution will be at the top. That is what is called as supernatant solution. Try to decant the supernatant solution. Okay, and then what you do is filter the PPT through the Bucknell funnel. Filter paper number, as I already told you, it's Wattman filter paper 1. Now what you do is, once you get the PPT, now to that particular PPT, you transfer that PPT in a beaker, add into it 5 cm cube of acetylacetonato, okay, and allow it to stand for some time. Slowly and steadily, shiny red crystals of Tris-acetylacetonato ion develops. Keep the beaker on an ice bath for some time, say for around 15 minutes and so. Okay, and then these cool crystals are being filtered through a Bucknell funnel using Wattman filter paper 1. And then once the filtration process is done, carry out the washing with water and alcohol. And finally the drying step has to be carried out. Okay, in a vacuum. Calcium chloride is there in a desiccator, which will absorb all the moisture, and that is resulting in the drying of the plant complex. And then finally, we are going to take the fate of the complex. Alright? So So this is my dear friends. In this first part of the video, I have tried to give you the theoretical approach of the synthesis of this complex. What exactly the complex is all about, what is the application of this complex, so why we are preparing it, okay, and then I have told you the steps which are involved in the preparation of this. Okay, in the next part of the video, I will actually demonstrate the procedure of synthesis of this complex. I hope everyone has understood up to this very well.